Okay, ladies and gentlemen, I'd like to welcome Bryan Cantrill from Sun Microsystems to talk about Dtrace.
All right, very succinct introduction, Paul. Thank you. So I'm Bryan Cantrill at Sun Microsystems, and I'm going to talk to you today about a technology called Dtrace. But actually, to kind of start off, maybe slightly philosophical, have you guys seen this book, Dreaming in Code, by Scott Rosenberg? You seen this? It sucks. Don't read it. I'm reading it right now. I'm reading it because actually the story behind reading it is actually along with some Google engineers, I contributed a chapter to a book called Beautiful Code, which I wanted to read when it actually came out because I only wrote a chapter. So I read Beautiful Code. I think I'm probably the second or third person to actually read the entire book, because if you read the entire book from cover to cover, you come away with some very different opinions than I think other people have come away with from. Anyway, that's it's a very kind of Beautiful Code's a very interesting book, but it's very discombobulated. You've got wildly disparate ideas of what constitutes beautiful code, and my assertion on my blog was that you can't possibly read every chapter and believe that every chapter is beautiful, because there are diametrically opposed, mutually exclusive definitions of beauty contained within that book. But I seem to be the only one who either has read the book or thinks that, or has any taste. I don't know. One of those three is true. Perhaps more than one. But so I always like to read books in twos. So I figured, well, it's been a long time since I've read a book on software, even though it's what I do for a living. I'll pick up this Dreaming in Code, which I knew was a bad idea. You know when you're on Amazon thinking to yourself, I know this is a bad idea. Why am I doing this? And yet that whole cycle of reading the book, I don't know about you. For me, I'm a finisher. Once I start reading a book, I've got to read it all the way through. And I'm just cursing myself all the way through. Why am I doing this? And it's a bad book because not necessarily because the writing is bad, although that also is true. It's a bad book because it's talking about a very tough subject in software. Software, and I assume most of us in the room have some interaction with software. You either build it, or you maintain it, or you deploy it into production. And software is really different. It is unique. It is different from everything else we have made. And when we try to draw analogies between software and other things that we build, those analogies always come apart. They're always loaded with fallacies. So what is it that makes software so special? And if you're curious about the book, the book is about this thing called Chandler, which is this open source Python personal information manager. And he kind of follows Chandler for a while, and then kind of like Apocalypse Now kind of goes up the river and starts wandering around the domains of software, kind of getting hoodwinked by every long-known crank in software. People like Alan Kay and so on are able to put him under his spell. And those guys, I have to say, no offense to those kind of folks, but I think that software was so new when they started to work on it that they didn't understand just how different it was. And people kept trying to draw analogies between other domains of engineering. So what do I mean by software being unique or special? Software is, here's the paradox. Is software information or is software machine? Exactly. The answer is it's both. Like nothing else. In software, the blueprints are the machine. There is no day labor in software. Right? For those of you who live in San Francisco, you don't go down to like Cesar Chavez and pick up 8 guys, throw them in the pickup, and have them go implement a linked list. It's not the way it works. Right? Because in software, once you've designed the thing, you built it. The design is the machine. That's why the waterfall model is so fundamentally flawed. This idea that you could design the design before you design it, which is what the waterfall model is essentially saying, is flawed. Software is both. It's both information and machine. And this is a point that was hit home to me when I first came to Sun 11 years ago. And I first came to Sun to work with an engineer called Jeff Bonwick. Jeff developed the ZFS file system, which you may have heard of. And so I was in Jeff's office, and I'd been at Sun for like 3 weeks, and fresh out of school. And we're debugging some problem. And we've got the source code up in one window, and the debugger up in another window, and we're kind of making progress on the problem. And all of a sudden, Bonwick kind of steps away from his keyboard, says, "Does it bother you that none of this actually exists?" And I'm like, come again, help me out. Where are we going with this? So we're looking at the source code over here, we're looking at the debugger over here, and we think that we're looking at a thing. This isn't a thing. This doesn't exist. We're not seeing an actual manifestation. We're seeing a representation of an abstraction. This does not exist any more than your name exists. Your name doesn't exist. We made it up. Doesn't this bother you? Like, well, it bothers me that I've only been here for like 3 weeks and you're going completely mental on me. I mean, that definitely bothers me. And I guess Jeff was just having one of those moments. But it's, when you think about it, it really is troubling. It really is very different. And it really, it does set software apart. In particular, as far as I'm concerned, one of the most immediate manifestations of this is we can't see software. What does running software look like? It doesn't look like anything. It doesn't emit heat. It doesn't attract mass. It's not physical. It is mathematical machine. And that is the problem, by the way, with all the thinking around software engineering has come from the gentlemanly pursuits of civil engineering. You know, kind of men in top hats who would employ billions to make, to build bridges and dams and so on. It's very romantic, but it has no analogy in software. That's not the way software is built. Software is much more like a bunch of people sitting around trying to prove theorems, many of which are irrelevant theorems that no one actually cares about, but nonetheless, that's a much better analogy. So in terms of seeing software, if it doesn't emit heat, if it doesn't attract mass, how do we actually see it? Well, we see it generally by actually modifying our software, right? By saying printf, we got here. If debugging printf, we got to this function, whatever. Here's the problem with doing that. You're modifying your software such that it is emitting a datum, right? And the problem with doing that is that it costs. Now you can say, like, well, I put this in an if statement. If debugging enabled, then printf. That doesn't cost very much. No, it's true, it doesn't cost very much. But it's still a load to compare in a branch, right, in terms of the microprocessor. Can't get around that. And you say, well, OK, so fine. Yeah, you're right. That costs too much. It doesn't cost too much if I do it once. But if I do it in tens of thousands of places, if I do it all over my code, I've got code that's too slow to ship. So what do? You conditionally compile, right? If def debug, if def tracing, if def I want to see my software, then if logging printf, or whatever. Now you've bifurcated your software. You've got two versions of your software. You've got the version that you can see, that you develop on, and you've got the version that you can't see that you put into production. And when you put that software into production, or that the ISV ships to you, right? When you're buying software from someone else, they've stripped out all the things that would allow them to understand their software have largely been stripped out because they made the software slower. So in order to be able to see software, we make it slower. That's a really tough burden to bear. And it explains part of why we have had such difficulty in software, because you get these abstractions layering on top of one another. Right? That's another thing that is very unique about software is this notion of the layer of abstractions. Because when you're at a higher layer of abstraction, you can do more and more and more as you go up to those layers. But you have less and less understanding of what's going on beneath you. And when the whole thing misbehaves, you can't see any of it. So what do? Well, the load and compare and branch is obviously out. And many years ago now, I and a couple of other engineers at Sun, Mike Shapiro and Adam Leventhal, began to think about this problem. What do we need to be able to do? What we want to be able to do is walk up to a system running in production. And we want to be able to dynamically, on the fly, change the text that is being executed, change the program text of either the operating system kernel or running applications. And we want to change that text in such a way that that it will emit data. We want to take that data and process it, understand the problem, and when we're done, we want to change the text back to what it looked like, fully optimized. Now, debuggers have done text modification for a long time, but the human is not in the loop here. And so this is what we did with Dtrace. Dtrace is a facility that originally we shipped in 2004 and has been shipping now for many years. That allows you to dynamically instrument the running operating system kernel, running applications on top of it, and to stitch it together. There we are. I guess this is the screensaver is some random presentation. No, that's. Am I that boring? All right. Hey, wake up the guy behind you. He's kind of drifting off. I know I'm boring, but I'm not that boring. If you read the book, you'd be ranting like this as well. So that, in short, is what we did. And so what I'm going to do this morning is just give you a quick introduction to Dtrace and kind of show it running on this live system here, my little Solaris laptop. And then I'll take you into where we've gone with Dtrace since we've actually shipped it. and talk about some of the problems that you might have and how it can be relevant to them. So this is my little Solaris laptop here. And one's introduction to Dtrace is just to run Dtrace. You see a very kind of Unix-y style help message here. And what I want to do first is just list the probes in the system. It's dtrace -l. So what this is going to do is list every point in the system that we know how to instrument. So we can see lots and lots of probes flying by. Now, and in fact, we can maybe actually want to pipe that to WC. So we can see on my laptop, I've got 50,489 points that we know how to instrument, probes. Now, what does that mean? These are points that the system has determined can be safely instrumented. This brings up a very important constraint on Dtrace. Dtrace is designed for production systems. As a result, Dtrace use must be absolutely safe. So we are analyzing the text, and we are determining places that are in contexts that are known to be safe that we can instrument. We can see we got a whole bunch of probes here. And I'm going to list the probes again. And actually, we'll just pipe this through the head here and see what this looks like. So in terms of this output, we've got a couple columns here. The provider column denotes the fact that in Dtrace, one of our observations was that we were always coming up with new ways of instrumenting the system, new kind of instrumentation techniques. And we wanted to separate out the way you instrumented the system from the larger framework that consumed that data. So that's what we did with these providers. And each of these providers knows how to instrument a different portion of the system. The syscall provider, for example, knows how to instrument the system call table. So you can see system calls. This FBT provider up here is the function boundary tracing provider. It knows how to instrument every function entry and return in the kernel. We got a lot of providers, and we'll get into those in a second. The module column denotes the kernel module for a kernel level probe, or the user level shared object for a user level probe. The function denotes the name of the function, and the name denotes the name of the probe. So we can see here we can see here we have me. I'm over there. That is me. I am pointing to myself there. So if we could actually get my laptop back, maybe not. So actually, I can see myself. If you can pause. Oh, there we are. All right, good. Thanks. Didn't have to. That was actually interesting. I felt like that scene in Spaceballs. So now I'm going to list the probes again. And this time I'm going to fully specify what we call the probe tuple. These 4 elements, the provider, module, function, and name, form what we call a probe tuple. And I'm going to list them again. And we separate this with colons, is the kind of the canonical computer science thing to do. And so this is going to list every probe from that syscall provider. So this is a shorter list. Probably a couple hundred here, however many system calls we have these days, 230. So far, we've just been seeing how the system can be instrumented. Let's go instrument it. Enough of this kind of horsing around here. To do that, all I'm going to do is strike that -l. So when I delete the -l, instead of listing probes, I'm going to instrument the system. And this is just going to instrument every system call entry with the default action, which just indicates, hey, you came through here. OK, so we're seeing every system call as it happens on the box. Now, on the one hand, this is actually pretty interesting. We actually, believe it or not, before Dtrace, didn't really have a good way of doing this on a production system. You say, wait a minute, hold on, that's not true. You have truss, you have strace, all sorts of things that show you system calls. It's true, those things do show you system calls on a per process basis. What those things do, truss and strace on Linux, they're automated debuggers. What they do is attach to a process, they instrument its system call table, that is, say, the system call points in that process using either ptrace on Linux or proc on /proc on Solaris, and they stop the process every time it makes a system call. And then your strace or truss prints something out, it runs the process again, it stops when it hits another system call. So the 2 problems with that. First of all, the probe effect is ginormous, to use a technical term. So if you've ever had a performance problem, and you've gone to use strace or truss on that problem, you will often discover that you have a new performance problem called you're running truss or strace on your process. Right? It'd be an enormous, enormous probe effect. And the other problem, of course, is it's only on a per process basis. Now, I've got to ask, have any of you been so desperate to solve a problem that you've tried to truss or strace every process on the system? You can do it if you want to, right? And Solaris, truss minus p, backtick, p grep minus d, comma, quote, quote, backtick, that'll do it. That will truss every process in the system. Now, of course, you probably have forgotten that you're running on your X server or whatever. Your whole system is going to basically grind to a halt as everyone is going in and out of the debugger. You're going to be walking into the next queue being like, hey, can you just SSH into my machine and kill off my processes? Oh, did you You didn't trust your X server again, did you? No, listen, all right. So if you've discovered this, it's very, and if you're trying to find a problem using that, you probably didn't find your problem. You introduced another problem, which is really painful. So what this is showing us, this is not showing us on a per process basis. This is showing us system-wide the system calls that are being executed. And we're not stopping anybody. They're zipping right through the system call table. We're just making a note off to the side. So this has got much less probe effect, and we're seeing a system-wide view. Now that said, it's not actually that interesting, right? It's like you've got writes and ioctls and polls. I mean, unless you had some bet with the summer intern that LWP sigmask isn't called or something. I mean, I don't know what you would. I don't know how this could possibly be useful, because all you're showing really is the system calls that somebody is making. So we actually want to record some interesting information with this. We don't want to just know the fact that someone somewhere is making a system call. We want to pull some data out of the context when that system call is being made. And this brings us to an important design decision in Dtrace, because we realized that no matter what data we would predefine to be available, you would want some other datum. And as these things usually work, you would want that datum on the worst day of your life, because that's usually the way these things work. It's like that day when you've got the production problem where when you got one of those days where you have a problem, and then you go to diagnose that problem, and then you have a second problem in diagnosing the first problem, and then you go to diagnose that problem, and you run into a third problem. This is when normally you don't scream at your computer, or haven't since you were in college or high school, and you start screaming at your computer, and your spouse begins to get a restraining order. At least maybe that only happens to me. But those are the kinds of days that you would want the datum that we didn't provide, right, when you're debugging that third problem. So we realized that we couldn't provide predefined data. What we needed to do is allow you to gather arbitrary data. And of course, that arbitrariness implied a programming language. So what we did is invented a very simple C-like, awk-like language called D. Not the D from Digital Mars, by the way. You're familiar with that D. Different D. Actually, funny story with that D. We invented our Ds roughly in parallel, not one of us knowing about the other, if you know about the Digital Mars D. And at one point, they mailed us implying that we actually need to back off the name D and that legal action might be just around the corner. Just had to be reminded that you can't actually copyright or trademark a letter of the alphabet. It's just otherwise, Microsoft would own us all, if not Google. Anyway, so we've come up with a C-like language called D that allows you to record arbitrary information here. So what I'm going to do is attach a clause in D to trace the exec name, trace the name of the executable. Now what we're going to see is actually, that was a listing. Let's not do that. Let's try to actually instrument the system. Now what we're going to see is more useful. PowerNowD and Xorg and mixerapplet2, whatever the hell that is. And send I don't know what, sendmail's here. We're not plugged into a network, but sendmail's doing something. All right, this is more useful. This is much more useful. So what do we see here? Dtrace, GNOME terminal, Dtrace, GNOME terminal. What are we seeing here? We're seeing us. Right. We're seeing all the system calls that it takes to write all this shit out to the screen. Not really all that interesting. Indeed, I would actually call this the top effect. Do you use top? When you run top, what's the top process? Top. Top's like, hey, man, good news. I found the problem. I'm the problem. Huh? Who would have thought that? Don't run me. It's like, all right, top, listen. It's true you have become the problem. But you were not the problem when I endeavored to find out what the problem is. Actually, it's funny. I was talking to one customer about this. A customer in the financial services sector where you think they might know better. And no, that's not the top problem. The top problem is we log into one of our boxes, run top, and the top 8 processes are 8 different tops from 8 different admins logged into the box trying to figure out what's going on. So, sorry, one or more tops. That's the top problem. And indeed, that is a problem. And the reason that's a problem is because of the methodology that top uses. Top goes around to every process and it asks it a question. Does not scale with the number of processes. You have 5,000 processes. Top is going to be the top process. By the way, we've got a much better implementation of top in Solaris called PRStat. If you haven't used that, and PRStat's got less of a probe effect, but still has a significant probe effect. So we wanted to get away from that in Dtrace. And we wanted to get away from this idea of when you're using a tool to understand the system, the tool itself becomes the problem. And so when you look at this data, this is not actually answering the question that one might have had. Right? I actually don't need a datum every time we do this. What I actually want to know is what processes are making system calls in my box. And so what we did is we developed aggregation as a first-class notion in Dtrace. And we denote an aggregation with this @ sign. And we can aggregate on an arbitrary tuple. In this case, I'm going to aggregate on the exec name. And I'm going to take the action to count. Now when I run this, I don't actually see any output, just that we've matched the probes. And what we are doing in the system, we've instrumented the system, and every time a system call happens, we're indexing into a table based on exec name and just bumping a count. Much, 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 much less probe effect. When I Control-C it, I get the answer to my question. Now, this laptop happens to be idle, so Dtrace is popping up more than it otherwise would. Actually, we'll make the laptop do a little bit of work here. So if I click around and da-da-da-da-da, there we go. And we can see that there's a bit of a party going on my laptop, actually. A bunch of things, like X screensaver, that's here. OK, don't know why we're running the screensaver. Metacity, trash applet. Oh, good. Yes, trash applet. Please, you need to do a lot of work. Please, have at it. What is the trash applet doing, actually? And actually, you may discover that, may already discover, in Dtrace, as in good cocktail conversation, the answer to one question provokes the next question. You're like, really? Trash applet. 58 system calls over a couple of second period. What the hell are you doing? That's interesting. So we want to investigate one particular aspect of this. And in Dtrace, that's a first-class notion called predicate. So what I'm going to do is I'm going to add a predicate to this probe. Say, if our exec name is trash applet, great name. I don't want to aggregate on the exec name. That's going to be trash applet, one would assume. I want to aggregate on the probe func. It's going to be the name. The probe func is a D variable. It's the name of the probe function will be the name of the system call in this case. When I let that run for a second, presumably in Control-C, I can see that over that period of time, we did one poll, one read, and 2 ioctls from trash applet. OK, this is getting interesting. This is telling me what trash applet is doing. Now, if I just had one trash applet, I might be able to go off and use my traditional tools. But if I had thousands of trash applets running on this machine, it'd be very difficult still to figure out what's going on. Now, if I wanted to, I could aggregate by PID. We could do probe func and PID, actually. We'll see if how many trash applets we're talking about. Presumably only one. So here's our PID, and there's our count. But I want to actually know, let's take these reads, for example. What the hell is trash applet reading? It really is actually kind of odd. So what I want to do now is actually hone in on this enabling a little bit. Instead of every system call, let's just do the reads. And instead of aggregating on probe func, what I actually want to aggregate on is the user stack backtrace with this ustack action. So now what we're going to do is when this thing comes in to read, we're going to take a user stack backtrace and tell me where are we in this application. Oh, we're, of course, from panel applet factory main closure, calling Bonobo gener. I swear the GNOME guys either want to give everyone else RSI or love RSI. It's like how anyone types in that function name, I don't know. But here we can see we were coming through GDK event check and into X pending and into a read. Now this is interesting. And maybe I actually want to go off. And I saw that we had, we're at PID 100972 here. Up to this point, we've been instrumenting the kernel, right? Actually, let's hop up into the app and see what this thing is doing. Let's go instrument X pending in trash applet. So dtrace -n, I'm going to use the PID provider now. The PID provider is able to instrument every single instruction in every single running process, which is a lot of instrumentation. And what I'm going to do is instrument, we'll do X pending entry. Now what we're going to see is whenever this guy calls X pending, we will see output. I mean, this guy's not going to call X pending. Don't be obnoxious, trash applet. Bad demo. This is the problem with actually demoing things you've never seen before. All right, let's. OK, now, oh, I've got a feeling. So I think that, is it related to that? No. All right, it's definitely related to my input, though. All right, you call X pending when I, all right, interesting. So clearly when let's actually, let me trace it, let me do this. Printf called X pending at %y. We'll do a wall timestamp with the -q option. All right, now what we're going to see is whenever this thing calls X pending, we're going to see a wall timestamp. Now, if I stay away from my laptop, I don't think it's going to do it. Let's see if I kind of horse around here, do a little clicky clicky. Interesting. OK, so clearly, when I'm interacting with my laptop, we're calling X pending somehow. You could actually, if you were developing a budding paranoia that someone was coming into your office at night and screwing with your mouse, this is a little script that you could write and confirm that, aha, at 2 in the morning, at 2:37, someone was in here. It's like, dude, you were in here at 2:37. All right, leave me alone. That's how it usually goes with me, with the Jacques. I usually end up being the culprit myself. So OK, this is interesting. I'm actually interested to know, and clearly it's calling expending when there are auxiliary events elsewhere in the system from this GDK event check business. I may be interested to know, what does expending do exactly? I don't actually know that much about expending. Presumably, it's got to do with something pending with X. And for that, actually, I'm going to write a little more involved script here. I'm going to write what we call a D script. And we'll call this x.d. Actually, let's get that process ID first. So what I'm going to do is write a little script. User sbin dtrace -s. And we're going to instrument expending entry. What I want to know is, what does expending do? It kind of runs through the software stack. What does it do? So what I'm going to do is, when we come in here, instead of just printing out a timestamp or whatever, I'm going to set a thread local variable, which we denote with that self points to syntax, to 1. That's what self points to follow is going to set a thread local variable to 1. Then what we'll do is instrument every entry and every return in the process with the predicate that self at follow is set. So we're going to light up the entire process, but we're only going to see output when self at follow is set. Self at follow is only going to be set if we came through expending. Then, when we're done, if self at follow is set, we'll set self at follow to be 0. And actually, I only want to get one of these, so I'm just going to exit when we're done. All right, make that guy executable. Now, when I run this, there's going to be a pause. And in this pause, we are instrumenting every function entry and return in that process. So it's a big process, apparently. My God, it's a huge process. That's a very large process. This is going to be a very large number. OK, so we've instrumented this thing in 109,000 different places. And now I'll try to get this guy to do its tricks. OK, there we go. And now we're actually de-instrumenting that entire process in all 109,000 places. So now we can see exactly what we did from expending. Expending called underbar x events queued, which called underbar xflush, which called xflush int, that returned. Xflush then returned. We called x11 transbytes readable, and so on. It's a little hard on the eyes, actually. So what I'm going to do is go back into the script. And I'm going to set the flow indent option. And what this does is, when we see an entry, we're going to indent to the right 2 spaces. When we see a return, we're going to indent to the left 2 spaces. So now if I run that again, we're now going to go again, re-instrument the system in 109,000 different places. And it occurs to me that actually I think the power saving mode is actually biting us here a little bit, because this guy's having to figure out that we're doing a lot of CPU work when we're going to instrument them. And see if we can. And there we can see exactly what happened from expending. And there it's coming into that read. Remember, this is how we found that. Started from the syscall and worked up, right? And indeed, if we wanted to, we could actually instrument not just all of userland, but we could actually instrument the entire kernel. In fact, actually, let's go back and do that. And instead of just every entry and return, let's do every FBT probe as well. And actually, we'll just do this. You don't need to see the. We'll light up those PID probes again, make it a little bit faster. And now what we're going to do is, now we're going to match a bunch of points of instrumentation, 48,000 in the kernel. And oh, right, I got to make it do something. Keep waiting for it to do something on its own. And this is everything in the kernel that actually induced. So we can see there's our syscall entry. This is coming into a read. So this is all in the kernel now. And this is coming in for that ioctal. So all the stuff we saw before is pre-syscall work. Then we do the getf. That actually, could teach a seminar on operating system design and implementation and history with the output of things like this. That set active FD is kind of an interesting story. So what set active FD is denoting is that I am doing work on this file descriptor, I being a thread. We had a bug in Solaris that was in Solaris for a astonishingly long period of time. If you had an application bug where you were closing your file descriptors as you had another thread that was IOCTing them, reading them, and so on, you could die on kernel heap corruption. This is up until Solaris 2.6. We've subsequently patched this back to 2.4 and so on. But for an operating system that was supposedly multi-threaded, it was a bug that existed for a long period of time. In order to be able to solve that problem, you have to do something. When you come into the system call layer, you've got to make a note that, like, I'm operating on this file descriptor, whatever that note is going to look like. You've got to record the information that I'm operating on a file descriptor. You can't actually close this file descriptor until I'm done with it or until I'm out of the kernel. Anyway, so we can see it running all the way through its IOCTL, which is, if you're me, if you're a kernel implementer, this is really interesting and incredibly valuable stuff. For you as technologists, it's probably interesting, but in terms of your day-to-day work, it may be less interesting. How does the operating system kernel relate to what you're doing? Well, the operating system kernel is in charge of scheduling all of the resources on the machine. And if you want to understand how your resources are being used, if you want to understand how CPU is being used, you want to understand what I/O you're doing, if you want to understand how processes are being created and destroyed and so on, you've got to be able to instrument the kernel in order to do that. Now, you can instrument the kernel in terms of its implementation. But this is a bit hairy. I mean, if you wanted to know, for example, where am I being descheduled? Well, you could know that we actually deschedule you in one of three, or you can catch that you're being descheduled in one of several places. Or let's take it being in queued to run. When you're in queued to run, we will call set back to queue, or set KP to queue if you're above k preempt pry, or set front to queue. Now, you could go instrument those three places. That's a bit of a pain. What we've actually done is develop what we call stable providers. So in particular, there's something we call the SCED provider that provides points of instrumentation around things like, wherever it is, NQ. NQ, on CPU, off CPU. You don't have to know that we take you off CPU and either resume from zombie, or resume from inner. If you just want to know where am I being taken off CPU, you can say SCED off CPU. And actually, if we wanted to just aggregate on exec name, we could figure out the number of times that any process is being taken off CPU indexed by application. Now, you could do all sorts of interesting things from this. For example, if we wanted to know why is mixer applet 2 coming off the CPU? This actually may be a very relevant thing. Let's say you're developing mixer applet 2, which I believe does audio mixing. And you believe that when you're playing audio, you should be completely compute bound, never come off the CPU. I want to know, where, if I'm being taken off the CPU, where am I? We can say exec name equals mixer applet 2. I want to aggregate not on the exec name, say, but actually the user stack backtrace. This will tell me where I am in that application that's being taken off CPU. Now, this is, and we can see that this thing is being taken off CPU because it's deliberately giving up the CPU. It's calling pull. So if you thought you shouldn't be taking off CPU, actually, this is an interesting point. Because it was down here, right? Here is where we're being taken off the CPU because we're calling pull. Presumably, either I want to wait for something to happen. So fine, you were taken off CPU. Here, you were taken off CPU because you had the audacity to call a GST Sun Audio Mixer get volume. You wouldn't necessarily think that that would rip you off the CPU. Now, it'd be interesting to know what exactly happened there. So instead of aggregating on just the ustack, let's actually aggregate on both the user stack trace and the in-kernel stack trace. So this will tell us where we were in the kernel, and hopefully we can get that guy to come off CPU in the same place. So this is giving us two stack traces here. Ah, interesting. Here are two stack traces. I actually should have done it the other way, so you could have seen it a little bit better. In fact, I will do it the other way. Give you a better view of what's going on. And we can see that here we are calling. First of all, why is the thing getting the volume a million times? Oh, all right, that's, it's another day, another bug with Dtrace. I swear, you can. What's that?
It's fixed in your GNOME. It's calling to get its mixer applet, so it needs to check.
Is it really fixed in the newer GNOME?
Yeah,
Oh, that's pretty funny. Yeah, I found a whole bunch of GNOME bugs with Dtrace, needless to say. Actually, I'll talk about an interesting story in a little bit. But one of the things that's interesting about GNOME, and more generally about desktop applications, is they've been very spoiled by an embarrassment of riches in terms of CPU horsepower. And we have got actually a pretty interesting product that wouldn't be of relevance to you, but is of relevance to things like educational organizations, governments, and so on. A product called Sunray, which allows you to have completely brain-dead clients, and all of your server state is on the server. And it's very cool, because you can put your smart card in, session pops up, yank out your smart card, walk down the hall, pop in your smart card, session pops up again, playing your videos or doing whatever it is you're doing. Really cool stuff, great for many different customers in different environments. One of the problems when we did that we didn't really realize at the time, is that we were taking these applications that had this embarrassment of riches, and we were taking them into an environment, the server room, in which there's not an embarrassment of riches by any means. And what we found is that a lot of these desktop applications were doing a lot what this guy is doing, which is waking up periodically and doing work. And in the server room, you do work when you have work to do, the end. And we found a whole bunch of interesting problems. So this would be, and actually kind of an interesting story in that is we actually had a Sunray server. One of the first actual uses of Dtrace in production was a Sunray server in Colorado that was in a whole hill of hurt. And these guys actually came into my office because they wanted me to help debug it. This is, they start describing the problem. We're seeing this many involuntary context switches per second and so on. And would you help us take a look at this? And so I asked them, well, what version of the operating system are you running? Well, we're running Solaris 9. And so this was back in, 2002. And the thing is, by that point, Dtrace had not yet integrated into Solaris, but I'd already been using Dtrace myself for a year in debugging problems. And what you'll quickly discover when you debug a problem with Dtrace is it's kind of like watching TV with TiVo, in that there's no going back. You can like TiVo, you can hate TiVo, but you're not going back to pre-TiVo. Right? I mean, I don't even view TiVo as a thing anymore. TiVo is like it's just a part of modern living. It's like a roof. Right? I don't think about the roof. I'm not like, yeah, my roof rules. I love my roof. It's more like I don't like sleeping outside. Right? TiVo is the same way. I mean, and pick your your DVR or whatever, but the whole notion of putting you in charge of the information that you're gathering, which is what TiVo does. Right? I'm now in charge. You're not in charge. Corporate scheduler. Same way with Dtrace. So I told these guys, listen, I didn't give them the whole TiVo spiel, but if you want me to investigate this problem, you're going to have to run Solaris 10 on that box. This is a box running in production. And the problem with that, of course, is that Dtrace only existed in a prototype form. There's no way they're going to run a prototype in production, so that was kind of the end of that. So I come back in my office 3 days later. They're like, OK, it's running. You want to take a look now? What do you mean? What's running? What are you talking about? It's we told us that we should run the Dtrace prototype in production in Colorado, so that's what we did. It's did I use the imperative? Did I say run the did it boot? It's yeah. Why, should it not have booted? I'm like, no, that's cool, that's good. I'm just it booted. We're all happy. I'm happy it booted. You're happy it booted. All right. So now I'm all right, shit, now I really have to take a look at this thing. So much for procrastinating. So I hop onto this box, and the first thing I did, and I don't know how many of you have any Solaris experience, but the first thing I did is the first thing that basically any Solaris admin would do when they're looking at a box, which is run this little command mpstat. And there are analogs in every system, right? Just give me kind of a one line of output per CPU. What is this thing doing? Just give me a basic idea of what this thing's doing. And this particular box, 10 CPUs, 32 gigs of memory, 172 some odd users, something like that. So big box at the time, certainly. This is a couple years ago now, almost 5 years ago now. And I looked at this output, this mpstat output, and it failed my most basic test for the happiness of a box. And that is, quite simply, in this output, God intended the columns to line up. And if you haven't ever seen this, this might not mean anything to you, but many a Solaris box, you'll run mpstat, and it's output is all over the place. You've got some 9-digit number kind of floating out here. You've got no idea, you can't even line it up anymore. You got no idea what it is. And so literally, this is my algorithm. I'm going to column 0. I am going to proceed to column n. The first statistic that overflows its column, we're going to figure out what the hell you're doing, and then we're going to make your column line up, and then I'm going to the right. And then we're going to get all the columns to line up, then we'll figure out what's wrong with the box. All right, so start with CPUs. We've got 3 digits here. We have plenty of space. It's fine. No, only 10 CPUs. OK, this minth column, these are minor faults. Right? So a minor fault is where you've got a mapping in your address space, but you actually took a page fault on it. Didn't have to do any I/O. We had to take a page fault. And we've got 4 digits here. And we're seeing a couple thousand a second. Fine. Major fault. A major fault is where you take a page fault, but we actually have to go to disk to actually resolve the page fault.
We're only seeing like 30 of these a second. We only have 3 digits here, but we're seeing very few of those. That's not an issue. Xcall, this is the cross-call column. This is one CPU getting the attention of another CPU by sending it in either an interprocessor interrupt in x86 speak, Mondo, and Spark, but in any case, interrupting another CPU. We have 4 digits here. That gives us a maximum of 9,999 cross-calls, and here we had our problem. This box was routinely seeing 12 to 15,000 cross-calls per second per CPU. And I asked myself the question that we have asked ourselves for time immemorial in Solaris kernel development, namely, what the hell is causing all the crosscalls? Now, we know what causes crosscalls, and if you're interested, I can give you the 7-part seminar series on what causes crosscalls. Crosscalls are typically caused, by the way, due to TLB shootdown, due to a DMAP. Right? So when a DMAP comes in, we've got to go actually invalidate that entry in other TLBs, and that's a crosscall that has to happen. That's the typical reason. That's what you hope is causing the crosscalls. But we kernel developers always get fidgety when this number gets high. And the reason we get fidgety is that there are some back corners of the operating system where we have to do crosscalls to work around some very nasty problems. If you're interested in one of them, actually, this is somewhat of an interesting technical issue. So Spark microprocessors have what's called a virtual address cache. So it's a virtually indexed, physically tagged cache. Right? So normally, on an external cache is physically indexed, physically tagged. And but the Spark microprocessors have why would you have a virtual index and a physical tag? Because you can begin doing the cache probe while you're still translating. Right? So you go in parallel to the TLB unit on the chip and your L1 or L2 cache. You're starting to probe that thing. Then when you know you've got a line, you wait for the TLB and then you can match the physical tag. Saves you cycles. This is usually on an L1 cache where your cycle count is very, very important. Where the cycles are the number, basically the speed at which you can execute. The problem with the virtually indexed physically tagged cache is that if the cache size is larger than the page size, you can end up with a really nasty problem called a back alias. That is where you can take the same page, same physical page, and map it at 2 different virtual addresses that do not map to the same line in the cache. They're what we call a different color. If the colors do not match, then you could have the same datum present in both halves of the cache if you have 2 colors, or multiple places if you have more colors. This is bad. This is very bad, because this is data corruption, right? And these are hard problems to debug. You have to take my word for it. If you had to debug them yourself, then you know how bad these are. So we don't want a back alias to arise. So when you do an mmap, what's on Spark at least, or on microprocessors that have virtually indexed physically tagged cache, when you do an mmap, you're letting us pick the virtual address. And so we're going to always pick a virtual address for you that lines you up with other ways that this physical page is mapped, so you don't have to worry about it. But mmap, and this is a good example of how very subtle additions to an API can lead to really nasty problems. When they developed mmap, somebody somewhere thought it was a good idea to have a map fixed option, a map fixed flag to mmap that says, no, I want to map this here. You don't get to pick the virtual address for me. I'm a smarty pants, and this is where I want to map it. Well, the problem, Mr. Smarty Pants, is that you can actually map your physical page in such a way by having 2 different processes or mapping fixed in the same process, same VA range with 2 different colors. You can create your own back alias. So we don't actually, there's not an errno with there's not like an E bad idea that you can return from mmap. Or E, you don't know what you're doing, trust me. You have to just I'm telling you to mmap it, you figure it out. You're like, all right, jackass, you're going to get your mapping, but you're not going to like it. And what we do in particular is, for that context, no VAC for you. No virtual address cache for you. L1 off. Sorry. And so whenever we see a hurricane of crosscalls, we get a little bit fidgety. We think to ourselves, you're not doing map fix anywhere, are you? It's like, no, why? Is that important? It's like, no, that's cool. Just because we're always a little bit nervous that all of a sudden it's good to turn out oh yeah, Oracle was doing that, and now the performance is 1/1000th what it used to be, which is roughly the kind of performance degradation you'd say. And there are other as arcane uses of crosscalls. So this is what's going through our head every time we're seeing this crosscall column. And the reason I go through that in some length is because we have not. This is going through our head because we have historically not had a way of investigating this on a running system. What is causing the crosscalls? With Dtrace, fortunately, it's very easy to investigate this because each one of these statistics has a probe that corresponds to it in the kernel, one of those stable providers that I mentioned. So in particular, Actually, I'll list the probe first. There is an xcalls probe from the sysinfo provider. The sysinfo provider makes available these probes that you see with MPstat. So if I want to know who's causing the cross-calls, it's that. That's it. And I would hope that we're on a uniprocessor, so I don't think we're going to be causing any cross-calls. It's a relief. You never know. So we're not seeing any cross-calls on a uniprocessor. Yeah, like I said, you never know. I wouldn't be surprised at all to see it's like, oh, it's my code making cross-calls. Why is it doing that? But when I ran this on this big box, this big 10-way box, I discovered that the X servers were making cross-calls. A bunch of X servers. And this wasn't actually that surprising because the Sunray model is that you're running all of your desktop processes are running on that server. So everyone's got an X server process. You've got 170 X server processes. It would make sense that they're doing most of the work, right? But why were they inducing the cross-calls? For that, instead of aggregating on exec name, just aggregate it on a stack backtrace. And you add a predicate in there that I'm only interested in the X server, ran that for a second, looked at the output of that. And to our relief, it's not because of VAT conflicts and mapfix and so on. It's because of the common case. We're doing a DMAP. We're in the munmap code path doing a DMAP. It's causing a TLB shootdown. Why are we calling it munmap? That seems odd. And for that, normally that would be a very tough question to answer. But actually, let's see if we can. We're looking at this process, I should say, when they were doing munmaps over and over and over again. So when they're doing mmaps over and over again, you detracing the mmap system call. Sure enough, you're seeing a bunch of mmap activity. What exactly are we mmapping? And for that, I looked at the argument, and I think it's FD's at 4. This is going to be. This is a bit dangerous to do this without looking at the man page. I'm sorry. That is not. Rather, actually, let me. I'll write that. Actually, I'll write this the way I wrote it originally, which is this. I'll take it back. I'm not going to write it that way. All right, I'm going to the man page. Leave me alone. I think it's arg 0, 1, 2, 3, 4. Damn, I was right. I just forgot the arg. Oh, such a tragedy. Should be args. That should be 4. That should be arg 4. All right, there we go. So what I'm doing now is I am instrumenting mmap entry, and I'm looking up the file descriptor arg4 into FDs, which is an array that we provide in Dtrace, and getting the FI path name. And this is a well-documented structure. This is all in the documentation. And now, when I Control-C this, I should see that we're mapping nothing. That's not very interesting. Let's kind of. This is what we were mapping over that period of time. And what does none mean, by the way? It means that, in all likelihood, we're passing a -1 for the file descriptor, right? Which means map anonymous memory. And indeed, that's what we saw. We were mapping here was anonymous memory. What's anonymous memory is a memory that doesn't have a file backing, and it is thought to be a cheap way of allocating memory is to mmap anonymous memory. The reason I say cheap and put it in giant quotes is because it's actually a lot more expensive than just calling malloc. But this is an example of where knowing too much can be harmful to you. And there are good reasons for that. The operating system has to do a lot of work to actually set up a new memory mapping. There are reasons to mmap dev0. There are reasons to mmap anonymous memory. But the performance is not one of them. It's because you're in a context that is too delicate to be able to call malloc. So looking at this, we saw that we were mmapping dev0. We were mmapping anonymous memory. OK, this is interesting. Aggregated on ustack, on the user stack backtrace, what do we see? We're mmapping dev0 from the pixmap creation code in the X server. OK, now we understand what's happening. We're creating pixmaps in the X server. When the X server is creating pixmaps, it's calling mmap of dev0 because it thinks that that's faster, even though it isn't. It's mmapping dev0. When those pixmaps are destroyed, it's munmapping it. When it munmaps it, that's causing the TLB shootdown, cross-call, and that's causing the column to overflow, and God becomes angry. OK, now we have the full path from pixmap to angry God. Here's the problem. That's not the full path, right? Because fine, one could say the bug is that pixmap creation destruction code should be calling malloc and free, not mmap and munmap. Fine. That's not actually the bug. Right? Who is creating all these pixmaps? That's actually the more interesting question. And to answer that question, I actually wrote a slightly more sophisticated script. We'll call this whommap.d. And what I did is I said, let's come into mmap entry. And if we are the X server, I'm going to say I'm interested in you. This is an X server that has done an mmap. Actually, this is when it was called xsun. It's now called xorg, so we'll actually change that to xorg. Changed our X server a while back. And then what I use is one of these sked probes, in particular sked wakeup. Sked wakeup fires when one process wakes up another. So what I'm doing is I'm saying, when the X server does an mmap, who caused me to do that mmap? That process is blocked on me in the kernel, right? Because it did an X call. So what I'm going to do is I'm going to do my mmap, fine. When I go to wake him up, I got him. And I want to know who that is. So if self@interested is set, I'm going to aggregate, and this makes available 2 arguments. One is the args0 is an argument that is the LWP we're waking up. Args1 is the process that we're waking up. So it's going to be args1, not in all caps. And we'll set self@interested. Actually, we'll do that after we set self@interested to be 0. We'll only get the first thing that we wake up. That's it. And indeed, if I make that executable, and spell it correctly, that's PRF name, not PRBS info. Let's try it like that. Now are you happy? And now let's see if we can get the X server to do mmaps on my, thank you, X server, for doing very little. First of all, let's make sure we're actually doing syscall mmap entry. What's that? Yeah, well, that's what we're going to find out. Of course, if we can't get the X server to do anything, it's not going to be very interesting. But we'll launch Firefox. That ought to. Hey, now. Oh, the X server, of course, is not. Of course, if they've, actually, I'm recalling, of course, that they have changed the X server to no longer do this. So the X server is probably not going to. The X server will no longer do mmaps for pixmap creation and destruction. So I would actually have to be lucky to catch the X server doing mmaps. All right, that's not actually going to work on a live demo, but we can, just because the X server doesn't do this anymore. So let's just get who's doing X calls. Forget syscall mmap. We'll just do sked wakeup if the exec name equals xorg. We'll just aggregate on who we're waking up. This will actually just give us a rough count of who's doing what on the box. And that should do something. There we go. So this is actually a rough indicator of who is making X requests on the box. And the interesting thing is when I ran this, I didn't see Firefox bin over here at the top. I saw so looking at this output, so we were seeing now the number of mmaps induced by different X applications. The second largest number over this 10-second period that I ran it was actually Metacity, and it was coming in, or Metacity as I call it, coming in at like 700, 1,000, something like that. And the number 1, with 6,600, if I recall correctly, induced mmaps, GTIC2 applet 2. So I don't know if anyone knows what the hell GTIC2 applet 2 is. I was asking myself the same question: what the hell is GTIC2 applet 2, and why is it trying to murder this box? GTIC2 applet 2, as it turns out, is a stock ticker application. And it didn't take too many further aggregations and so on and looking at stack traces to figure out that GTIC2 applet 2 was waking up. I wanted to actually wake up once every millisecond, but due to the scheduling granularity in the system, could only wake up once every 10 milliseconds. Every 10 milliseconds, what would it do? Create a graphics context, draw a pixel, and destroy the graphics context. Now, for software developers, this is something of a capital crime. And there have been several. This is special circumstances, the works. We've got there's several things here that constitute capital crimes. One, you're waking up every millisecond on when you should know the scheduling granularity is every 10 milliseconds. And what do you need to do every 10 milliseconds anyway? I mean, aren't we talking to like a stock quote that's being updated like every 20 minutes? I mean, do we really need to be waking up several hundred or 1,000 times a second if you had it your way? One. Two. So we're drawing a pixel to the screen as if this were like a military flight simulator, for whatever reason, instead of just someone seeing how underwater their options are, in my case, and above water in your case, perhaps. But the third thing, of course, is that we're creating a graphics context, drawing a pixel, and destroying the graphics context. If you've done any X programming, so graphics context is a server-side resource you use to draw. And when it's first introduced in your X manual, there's like one of those big caution signs, like slow down, knucklehead. graphics contexts are server-side resources. They're precious. You create them at the beginning of your application, do all your drawing, destroy them at the end of your application. Don't create and destroy these things with reckless abandon. But the orangutan that wrote GTIC2 Applet 2 apparently skipped that chapter and proceeded to create graphics contexts. Tried to create graphics contexts 1,000 times a second, only succeeded in 100 times a second. There were 6 of these running on the box, and it was murdering the box. And to see just the degree to which it was murdering the box, there's 3,000 processes, by the way, in this box, and 6 of them were doing all of this damage. I p-stopped the 6 GTIC2 Applet 2s. And that MPSAT output I showed you, it was like a hurricane blew over. Not just that column, but every column lined up. The system time, if I recall correctly, dropped by 30%. Idle time skyrocketed. Cross calls plummeted. Cross calls went from 12,000 per second per CPU to 1,000 per second per CPU. We were able to put 20% more users on that box at much lower latency. Big increase in throughput, great drop in latency. And now you might say, it's like, OK, well, the problem is that we had an orangutan write GTIC2 Applet 2. And that is a problem, for sure. But I don't actually blame the orangutan necessarily, because this is a problem that's endemic to software. When you're building, this is what those layers of abstraction I talked about. You're up at those very high layers of abstraction. And it's like, literally, there are 2 lines that need to be hoisted out of a for loop. Those 2 lines caused Sun quite a bit of monetary damage. So in terms of, and this was in 2002, I should say, when I think things were just changing in terms of the languages that people were deploying into production. Right? So in 2002, people deployed a lot of Java, but things like Python, Ruby, so on, were still serving an auxiliary role. We're not actually running in production in anger. That's changing. And I'd be actually interested to know, how many of you have to debug, say, Python problems in production? Oh, you're going to be very happy. Really? OK, that's interesting. Because I mean, Google was the first company I'd ever heard of in, 99, when a friend of mine worked here, was mentioning that. It was like, yeah, they do a bunch of stuff in Python, and so I picked it up and started playing with it. It's like, wow, it's a really powerful language. So this is actually the first company that I heard people developing Python in production, more than just kind of in a supporting role. So it's no surprise that several of you are dealing with Python in production. How many of you do you see any Ruby in production? JavaScript? Perl? Wow. Java? Java, presumably? No? So is Python kind of the... Really? Well, that's very interesting. OK. So if you've ever debugged a Python problem, so even with Dtrace, you go to run Python. And here, let's actually do, got some Python here. This is a very, very, very simple program. So we're just going to loop around. And we'll call that guy. So if you had this Python running in production, and you're curious, what the hell is this thing doing? And actually, let's should actually, well, I can make that thing a lot more interesting. Let's actually make that a lot more interesting. Loop.d, cp loop.py, while1.py. So let's make this guy just spin out of control. How about that? That seems a lot more interesting. Funky, we'll just take out the sleeps here. Goodbye, sleeps. This may be a more accurate representation of what you see in production. All right, and actually, we'll run that over. Well, let me run that over in the background here. So let's say you've got Dtrace. Very happy, you're very excited that you've got Dtrace. And you've got this production box. And it's getting killed doing something or another. So now we're going to see, of course, we're going to be blocked a lot on the terminal. It's like, oh, Jesus, what's going on? The columns line up, fortunately, but God is still angry. And you run your usual, because you've got Dtrace and you're so savvy, you say, oh, this is a great opportunity. I can use Dtrace. I can aggregate exec name. What are we doing? I'm going to figure out who is murdering my box. Da-da-da. Of course. Python. I've got you now. I've got you now, Python. I am so close to understanding what this problem is Just going to do a little useStack action. I'm going to see the stack backtrace. I'm going to call up the Python developer. I'm going home. No, you're not. You're going to see a lot of this. I found the problem. I just need to find the guy who wrote call function. Call function? Call function. Look, it's recursive. This moron, what is he doing? Don't call yourself recursively. Call function? Stupid call function. And hopefully you don't actually raise this with any of your coworkers. Hopefully you realize, wait a minute, call function. Don't! Because you're not seeing, this is not like, there's not like call functions that's, this is not like, calculating, pi out to some number of digits. Call function is just executing Python somewhere. And even with Dtrace, what you had to do is go instrument the actual Python, the implementation of Python, to figure out what the hell is going on. So this was the state of Dtrace when we shipped it 2004. And we realized that there were all these environments out there, Ruby, Python, Java, and so on. And how are we going to go instrument those? So what we did is we developed a couple of interesting technologies that allow us to put zero disabled probe effect probes into these various environments. So and the way this technology works is actually pretty interesting, is we actually declare a probe site. That gets turned into a call that the linker then nops out but records the probe site. That gets all allocated down to the kernel. We know where that is in the application. We can turn that nop on. Now, what we discovered is with environments like Python and especially Ruby, even that wasn't enough because they had to do so much work to figure out where the hell they were in a function entry, for example. Ruby, getting the class name is like, it's like trying to get your tax return from 8 years ago. I mean, the amount of work they have to do to get the class name in Ruby. So for that, we invented something called isEnabled probes that allow you to say, if this probe is enabled, here's this block of code that I want to execute. Then that becomes a NOP site. And when that probe turns on, we make that go live. And now we're gathering this information. And you can hit the probe site with some really interesting information. What kind of interesting information? Let's take a look. If my laptop doesn't melt here, and it's trying to. What we'll see here are Python probes. And actually, I'm going to, no, I'm not. I was going to put myself in the real-time scheduling class, but I guess I won't do that. So what I actually want to go do is instrument Python star function entry. That will fire whenever we execute a Python function. Now, that's not necessarily that interesting, because I want to know what we're actually executing. Now, this probe has got arguments. And the arguments consist of, first of all, arg0 is the file. So if your first question was, what file are we in? Now, this would be the Python file. So if you've got a running Python that is this huge collection of modules, and you want to know, very simple question, I see this guy is compute bound. Which module is it? If I just knew which module it was, I would know which phone to pick up. So I can do that by just doing this. Aggregating on copy instar of arg0, take the aggregating action to count. And now in this case, it's all while one. Not necessarily that interesting. If I want to know what function we're in, what function we're calling, that's arg1. Func A, func B, func C. And actually, let me show you a script that a coworker of mine wrote, where we can actually do flow tracing through Python. So I'm going to use just those probes. And it's written by a guy named Brendan Gregg, who works for Sun now, but wrote something called the Dtrace toolkit. And I'm just going to run this sucker. And what you're going to see is the actual flow through the Python. Rather useful, actually. All right, so I'm going to stop my little while one goober over there. And let me actually, I'll run the loop here, because I want to show you something that's even cooler, actually. So it's great. You can now instrument Python thoroughly. One problem that we still have in many environments that we had initially in Java is this. That, OK, fine, I can instrument my Python and understand exactly what I'm doing. What happens when the point of instrumentation is in the kernel? What happens when I'm doing I/O, for example? I'm doing I/O, I'm in the kernel, I want to know where in my Python am I? Right, that user stack backtrace just gives you call function, call function, call function. Or RB eval, RB eval, RB eval. Which actually is kind of funny. You can tell people who have to deal with these languages in production because they see those names so many times. You can just kind of utter the name and watch the rage erupt. RB eval is a good one if someone has to deal. Ruby sucks in terms of performance, and you see a lot of RB eval. So I want to know actually where am I in my Python. This is really hard to do, and we had this problem with Java. And so the problem is this, just to restate it. We're in the kernel. We're coming off CPU. We're doing I/O. I want to take this stack backtrace and turn it into something that's meaningful for Java. The problem is all that information that you record in that stack backtrace, by the time you post-process it later, is irrelevant to the JVM. JVM's JITted things and recompiled it, whatever. So OK, all right, fine. So let's just go up to the JVM and we'll ask it, hey, here are a bunch of addresses. Like, can you tell me what the stack trace looks like? All right, that's all well and good. But hey, we're coming off CPU. All right, we're in the kernel coming off CPU. You can't even grab locks, dude. Like, you're coming. We are in a very delicate context. You can't go around running other processes. Can't stop anybody. So we can't grab locks. You're done. We've made the decision to take you off CPU. So what we did is something that is mind-bendingly complicated and took us a long time to satisfy ourselves that it was the simplest solution to the problem, because I generally hate complicated solutions, but this is a very hard problem. What we actually did is the JVM has something that we call a ustack helper. And it is a special D script that fires in the context of the actual enabled probe getting a ustack. And what it does is it allows the JVM, and then this D script is compiled into what we call DOF, which is the D object form. It sits in the JVM. When the JVM runs, it ioctls this down to the kernel. And when you grab a user stack trace, it executes these instructions, this virtual machine, to actually calculate the stack trace into something meaningful. These are very, very hard to write, and it took us a long time to get all this to work. But once it works, it's very powerful, because now you can correlate your Java to what's happening in the system. And so I actually wrote one of these for PHP to kind of prove to myself that it could be done for other languages. But I knew that, so basically I had effectively written the Java ustack helper. I wrote the PHP ustack helper. Like, there is no way anyone else on earth is ever going to be able to write one of these, because it's so delicate in terms of the context that you're in. But I was wrong, and I'm blessed with very talented colleagues. A guy named John Levin at Sun wrote a Python ustack helper that, even better than writing it, he actually integrated it. It's actually in Nevada now. If you were to download Nevada is the most recent version of Solaris. If you were to download Nevada after build 65, you will get John Levin's Python provider plus ustack helper. And this is unbelievably powerful, because now I can do things like this. Sched off CPU. Well, first of all, let's just aggregate on exec name. We should be able to find that Python guy should be over here. And he should be in here somewhere. There's Python 2.4. So let's say exec name equals Python 2.4. I now want to aggregate on ustack. And I'm going to give ustack some special options here. Normally, ustack just keeps a default number of frames to store. And I'm going to tell ustack, actually, I want you to keep a larger buffer for string data that's coming out of a ustack helper. And I'll just give it 8192 as kind of a nice round number. And now, when I Control C, so there's your py eval code, loop.py, line 20. Loop.py, line 17, func A. Loop.py, line 11, func B. Unbelievably powerful. And this is what you're seeing is effectively the deepest technology in Dtrace. And fortunately, it is technology that is very applicable to the kinds of problems that you are solving. And actually, I think this is the first time this has been publicly demoed. John did this work very recently, and Blog Dialects had integrated it. And I first learned about it from the blog entry. I couldn't believe. If you go to that blog entry, you'll see my first comment being like, I can't believe you managed to write this thing, because it is such a delicate context. But you don't have to worry about the technical details of writing it. As far as you're concerned, the upside is awesome, because you're able to actually understand what your Python is doing. So for you, it's going to make quite a bit of sense, I would assert, for some of your problems to actually have a box that can run dtrace with the Python ustack helper, and actually go, because Python Python sloshes between operating systems awfully well. And it will make sense for you for some of your problems because this is such an unprecedented level of production Python visibility, observability, to reproduce some of your problems on a box that has this kind of stuff and actually be able to understand what your Python is actually doing. So that is the, that's kind of, I think we've gotten till 11:30, right? Or am I over? I'm not over, am I? I'm over. I thought it was 10 to 11:30. 10 to 11. OK, I'm 20 minutes over. Sorry about that. Well, thanks for staying. I didn't realize that. I guess the more people I thought would have defected if I, all right, sorry about that. Well, you're late for your next meeting, but who cares? It's just a meeting. So with that, I'll open it up to questions. With my apologies, normally, like I said, I thought I had 90 minutes here. Yes?
So what user scored supporting Dtrace to
Sorry. Of course. Obviously, that's the question. That wasn't the question. I was going to go into the audience myself. Especially here. OK, yes. Great question. What is the status of Dtrace on Linux? So let me be blunt with you. The Linux is unusual in that it is upside down in terms of where its expertise lies. Normally, with a system like Solaris, your best Solaris expertise works for Sun. That's not true. The best Linux expertise, with some exception, does not work for Sun. And I think that there is more deeper Linux expertise at Google, at VMware, at Pixar, than there is at Red Hat and Novell. And feel free to disagree, but that's my experience. The Dtrace can absolutely be ported to Linux. It's open source. It's ready when you are. It's been ported to macOS. It's been ported to FreeBSD. NetBSD port underway. If you can, I shouldn't say it because I'm being videoed. If you could keep a secret, I would tell you another operating system is being ported to. But there's lots and lots of interest out there. Because people that are doing their homework are recognizing that if you actually start to take apart the technology required to get this to work, you ain't going to replicate it. It took us a long time to do this. We were very focused on it. We'd been thinking about this problem for a long time before we even started. And the Linux effort is hampered by several things. First, there is some fear, uncertainty, and doubt about the licensing issues. Those issues are not issues for you. You do not distribute Linux. You do not need to, the GPL does not apply to you until you actually attempt to distribute it. So you can port Dtrace to Linux and be scot-free. So can VMware. So can Pixar. So can these other companies. And I think it's actually licensing FUD because the GPL has never actually been tested in court. But there'll be disagreement on that. I don't want to diverge in a licensing discussion. I believe that one can make a very strong case that you can port Dtrace to Linux, distribute the whole thing, and actually be in fine shape. But others absolutely will disagree with that. You can certainly port Dtrace to Linux and use it internally. The second phenomenon that is hampering the Linux effort is just for personal pride reasons. Red Hat is interested in competing with Sun. Google is interested in solving problems that you have. So Red Hat is not interested in porting Dtrace to Linux because that would be this huge deference to Sun. So Red Hat has a rival effort to Dtrace called SystemTap, which unfortunately, I mean, it's great that they've been, that I guess imitation is the sincerest form of flattery. But is bad imitation that sincere a form of flattery? I don't know. And atrocious imitation, I don't think actually is flattery. Or I'm not flattered. Let's just put it that way. They don't understand the problem that we solve. The problem that they're trying to solve is Sun is kicking the shit out of us on Wall Street with Dtrace. That's the problem they're trying to solve. Not, I've got Python that's running in production that I can't observe. That's the problem you're trying to solve. Very different agendas. You guys don't, that's my knowledge, and you probably got some Red Hat kicking around, but you ain't paying Red Hat for all your 100,000 boxes. Right? Or if you are, I found a good way for you to save some money. Right? You're not a Red Hat customer. And there are lots of people like you that aren't. If, and I believe when Dtrace is to be ported to Linux, it has to come, we believe, from technologists at companies like Google. What will it take? Well, first of all, we'll help you. We understand the code very well. We understand, having worked with the FreeBSD folks, having worked with the Apple folks, we know what it takes to port it to another system. It's not easy. It's deep technology. And this is not something that we need more than just like, I'm interested in using Dtrace on Linux. Yes, we know. Lots of people are interested in using Dtrace on Linux. But if you can do the heavy lifting that's involved in actually getting it to work, we'll work with you. So what we're trying to do actually right now is put together a coalition of folks across companies that are actually using Linux that have the expertise to do it. If you're interested, we'll sign you up. And I think what we'll be looking for is you would probably need to be local in the Bay Area or be able to come out here for some period of time. And what we're thinking is like we get everyone together for a week and get in a conference room and see how far we can get. So we've got guys at Sun that are willing to take a week of vacation to do it. And I'm sure Google would be asinine if they wouldn't give you the week to do it. So if it's something you think you can do, and it's something you've got the technical ability to do, we're here to help you out. Because we think that the issues about not taking Dtrace to Linux are bullshit, for lack of a better word. But I didn't anticipate that question at all. I was totally caught flat-footed by that question. No, that's right.
I have a related question. Can Dtrace be ported to Windows?
Yeah, actually, absolutely, actually. I mean, the Dtrace itself is, in part, actually, because of the problem we were trying to solve, we have to operate in very constrained contexts. So it means we can't go calling kind of kernel services at large, right? We can't go call printk, which or the equivalent in Solaris. We can't really use the Solaris primitives that much. We don't use, I mean, mutexes, for example, synchronization primitives. We only use synchronization primitives in the infrastructure required to get Dtrace up and running. When you are actually in probe context, you can't grab locks in probe context. We run with interrupts off, right? So, and we've separated out that layer pretty well. So it's it can absolutely be ported to Windows. If Microsoft's interested, we're interested. Anyone that wants to port Dtrace to any platform, we are interested in working with to make it happen, because we think it's a win for everybody. It's a win for humanity. The technology can definitely do it. It's not easy. I don't want to say that it's not easy, and you can discover issues where it's like, oh shit, this is going to be really hard, because we built Dtrace on the foundation that we had built in Solaris for years. So we built Dtrace on some technologies that we'd spent a lot of time investing in at Sun. And the FreeBSD guys decided to take a bunch of that technology into FreeBSD, which is great. That might not be the easiest route for other systems, but it absolutely can be done. Other questions? OK, great. Thank you very much. And I'll, sorry, I should cut off my own applause. If you want to get a hold of me, I am bmc@eng.sun.com. And you can find my blog online. But if you're interested in contacting me, either come up and see me afterwards, and we'll exchange contact information, and let's try to get a Linux port off the ground. So with that, thank you very much.